throwing that all aside, welcome to this week's Graphics Programming
Yes.
Weekly. This week we're going to be covering shaders, the graphics pipeline, and finally cleaning up stuff in a delay deletion queue. There's a lot of text to cover, but thankfully there isn't that much code. Like there's code, but there's not a lot of complex, intricate stuff. It's mostly just initializing and filling out structs. So we got to understand the graphics pipeline before we can talk about it. This tutorial does not go into very large amount of depth, but it does give a cursory overview of what the graphics pipeline is. You can think of it as a pipeline with 5 stages, main parts of this, main stages. You have your data input, and this is all the data, not just a specific kind. And the first programmable part of the pipeline is the vertex shader. Shader here is a piece of code that runs on the GPU. We run it on some of the data, and then we rasterize the outputs of that shader. Rasterization is the process of turning vertices into pixels. So it's taking 3 vertices, drawing a triangle, and then putting it over a frame buffer and figuring out which pixels in that frame buffer need to be rendered, i.e. rasterized. So it will give us a list of pixels to draw, and then that we feed that into the fragment shader. A fragment is a pixel. It's more correct to say it's more like a possible pixel, because a fragment may or may not go to the final image, but we don't know yet. We need to render it first. So we draw all the pixels here. So the shader, that means it's programmable, and we run it on all the pixels. Once that's done, we take all the pixels and put it into the render output. This is the process in which we take our input data to the scene and turn it into a render output, or a image output. So shaders are GPU code. They have a restricted programming model. They're designed for parallelism from the get-go. So in a normal CPU program, if you want to do 2 things at once, you have to create a separate thread to do the thing. And CPU languages make it very, very difficult, for lack of a better word. But in a shader runs on a single piece of data at a time, but the GPU schedules the same shader to be executed on all the different pieces of data at the same time, because GPUs are massively parallel. So in a lot of ways, a shader is like writing, the shader code operates 1 vertex or 1 pixel at a time. And that makes it really easy to program for, compared to what's happening on the hardware, where you're getting 10,000 vertices being processed in parallel, and then 10 million pixels being processed in parallel. But so now we can actually look at what those vertex shaders look like. We need 2 shaders, the vertex and fragment shader. That's the bare minimum needed to render 3D objects. There are other parts of the pipeline that are also shaders, but we don't really use those as much. So we're probably not even going to cover them in this tutorial. I don't think so. Just vertex and fragment will do everything we need. A shader is GPU code, but code must be written in a language. The language we use is GLSL, or OpenGL shading language. It's very similar to C. It's more of a reduced set of C commands, or the C language, with added syntax that's for the GPU stuff specifically. If you look at the code here, we see a main, which has a return type of void. We got the curly braces like C. We have our macro define up here. This is saying that this shader is using GLSL version 4.5 or 450. And well, in the vertex shader, the only thing that we have to do is write to this magic global variable. So this is a special bit of GLSL syntax. This corresponds to the output position of the vertex. What we assign it is a vec4. So a vec4 is a built-in type. That's an array of 4 floating point numbers. Vec2 and vec3 are other built-ins. So we have vec3s over here. Like in C, we can have arrays. So we have our vec3 position of 3. So this is an array of 3. And what we're doing here is hard coding a array of vertex positions. So there is no input to this function. All the data it has is going to be baked into the shader itself. And we use another bit of OpenGL specific stuff, this vertex index. This is a global variable that corresponds to the index of the vertex that is currently being processed in the vertex shader. And well, the fragment shader is very similar in its structure. We got our void main and we got the GLSL 450. Now, there is no global variables here, but what there is an output variable. In not OpenGL, but in GLSL, you can have inputs and outputs that are per shader invocation. So here we have an output of type vec4 called outFragChord. An output on a fragment shader is going to go into the frame buffer that we want to write our pixels into. What we have to specify in addition to the name and type is this out keyword being the thing that signifies that this is an output variable. We have to specify the location, which is 0. This way we can statically define where our outputs are going to go rather than have to look up the name on the CPU when we're loading the shader. What this shader does is simply return a vec4 of the color red. So that's the red channel, the green channel, the blue channel, and the alpha channel. So we want red to be 1, meaning, and blue and green to be 0, so it's just going to be red. We need to compile the shaders because while GLSL is a shading language, Vulkan does not accept GLSL. It accepts SPIR-V. SPIR-V is a I forget what the acronym stands for, but it is a bytecode and not a text format. So we need to turn our GLSL into SPIR-V. Thankfully, the tutorial has actually set up a folder for us to put our shaders in. That way, and set up the CMake build codes such that we don't have to manually compile the shaders every time by hand using the compiler. We can just throw them in a folder and it will be automatically compiled. So if you want to know how that works, you can read the source code for it. And you could even extend it so that you could do this at runtime and compile your shaders on the fly. But that's more work than what we're needing to do, so we won't be doing that. The compiler for our GLSL to SPIR-V is in the Vulkan SDK, so we don't have to install anything extra. And we will be using that, or rather the tutorial will be using that. So it says to create the shaders now. Triangle dot vert and triangle dot frag. Come on. And we can edit these. shaders. If we build this, yeah, okay. It didn't like it. It did not like it at all, but that's because I don't think I put anything in here. If I edit edit the thingy, so bear with me. So this should be the fragment shader. Edit this guy, where is it? Edit. Copy and paste the code in. Then we rebuild the shaders thing. Okay. And it doesn't appear to be in here, which is interesting. It compiled it, but I don't see the shader code. Oh well, we'll just have to look at it in here for now. We've compiled it successfully because we put it in the folder where it will magically print out, or it will magically compile and put the output into a .spv file, and this is the files we need for running our program. We'll want to make a function for loading, and we'll put it in the Vulkan engine class. So we can down here, and it takes this file path and it outputs a shader module. Let's copy the, so we have our little shader module function. Oh, since we're loading a file, we're going to need to include the file stream header. That way we can access the various file streaming APIs. File streaming in C++ uses the, it's a bit out of scope for the tutorial. The gist is we have a file, we construct it given a path, we give it these two parameters. One of these is that it's a binary file because the output is a compiled binary of bytecode, and the other is 8, which means we want to start at the end of the file, or have the current pointer, read pointer is at the end of the file. This way we can read the size of the file, and that's what tellg does. And this gives us the amount of bytes that we need to allocate in a vector to make sure there's enough size such that when we load the file into a buffer of uint32s, there's enough space for it. For reference, SPIRV is a bytecode format, but it's not encoded in bytes. It's encoded in uint32s, or 4-byte chunks, or 4-byte instructions, really. So a SPIRV file will always be a multiple of 4 bytes long, which is why this will work. We get the file size, and we can divide it by this size, which is, it doesn't want to tell me, but it's 4. Once we've created the vector, we can load the vector into the buffer using the read function. And then now that we're done, we can close the file. And I put the seek in the wrong order there. So after we've gotten the size of the buffer, we need to put the reading position at the very start. It probably would be a good idea to put as assert, but it's not necessary. And the validation layers will probably yell at you if you get it wrong. Now that we've loaded the file, we can create a shader module for it. A shader module is a Vulkan object. We use the normal S type and P next. That won't do anything. Not do anything. There's nothing special there. The code size is the buffer size times the size of 4 objects. So this is in bytes, whereas this vector is a vector of uint32, or 4 bytes at a time. And then we give a pointer to that buffer in the P code variable. And that's the only 2 things we need to provide to create a shader module. Now, because shader module might fail and we need to know about it, instead of just asserting, we're going to return false, allowing someone to handle it if they wanted to. And we'll do that in a second in the function that calls this function. If we successfully create it, we write the shader module handle out here, which is an out parameter. Then that way we give them the module handle to use. We need to then have another function which will load or tell the program which shaders to load, as in their location. And because we need to do it once for the fragment shader and once for the vertex shader, we have to do it twice. This is red just because it hasn't determined. Oh, I know why, because I need to add the function over here. So that should make it happy. This is what I mean by error handling. Right now, we're just going to print out, yes, we succeeded, or no, we failed. Yes. If I hit F5, does it print stuff? It does not. Is there a reason it doesn't? Interesting. Well, we're going to ignore that for now and continue on. So now we get to pipelines. We've talked about shaders. Shaders are an integral part of pipelines, but pipelines are the amalgamation of all the state you need to render or to rasterize something in Vulkan. They're big objects. They got lots of things in them, and so we'll have a lot of structures we're going to have to set up. A VK pipeline is a stateful object in that not stateful, but it contains a lot of state that you set when you create it, and you don't get to change, as in it's fixed and you cannot change it later on. You have to create a new pipeline if you want to change any of it. That includes the shaders, but also sort of stuff like the rasterization mode and the depth and some of the blending modes. And some things are dynamic and are allowed to change after you've created the pipeline, and that's called dynamic state. And it's very useful because it means you don't have to create a new pipeline for everything that needs to be slightly different. Say you want to render a slightly smaller image this time, so you can, with a dynamic state, you can change the size of the output using the viewport. But not everything is like that, and we want to use as much dynamic state as is reasonable, because pipelines do take a while to build and they take up a lot of space. So you don't want to use too many of them, but you don't also want to use too few of them, as in there are places where it's better to have more pipelines than it is to try to minimize them. That's getting sidetracked. In the tutorial, we'll create multiple pipelines. We're going to create a pipeline builder, which helps us build pipelines. This will contain all of the state we need to set before we can build the pipeline, as well as a function that will build it for us. Because each of these things, like the vertex and input assembly, all of these things have their own initializers, we're going to add a bunch of initializers to the initializers header. Right now we just have 2, but we'll add a whole bunch more. I think I need to copy all this in and then delete that. So this is the pipeline shader stage create info. This is what hooks up the shader stages, our fragment and vertex shaders, to the pipeline and provide the shader module we want to use. So here we take in a stage flag bits, as in the stage, either fragment or vertex, and then the shader module handle that we created earlier, and it puts them into a struct and then returns that struct. Because we can configure the name doesn't mean we should. The default name by convention is main. This is the entry point of the shader. If we wanted to change it to this, we could and put it over here, but it's not necessary for what we're doing. The pipeline vertex input state is necessary when we are specifying the vertex buffer layout to use in the pipeline. You have to specify that ahead of time. Because we put the vertex buffer inside the shader, we don't actually have a vertex buffer. Therefore, we don't have to do anything other than provide the S type. Everything can just be 0. Gotta add this here. Similarly for the, no, not for the input assembly. The input assembly is something we do need to specify. And the input assembly's main thing is defining the topology. The topology is the way to interpret the vertices we've provided, but because Vulkan just you provide a fat array of vertices. How those vertices get interpreted is up to the input assembler part of the pipeline. It runs before the vertex shader, and the 3 different modes are triangle list, point list, and line list. We're going to use the triangle list for most of what we're doing, but these are also useful for other things, namely drawing points and lines. We're not going to use primitive restart. Primitive restart allows setting a specific value as an indice and then restarting which vertex you're using based on that. It's a bit advanced. You can look it up yourself on your own. Come on. Copy and paste it. Okay. So now we can get to the rasterization stage. This is the stage that runs after the vertex shader. And there's quite a few number of things we actually do want to set. Some of them we're just going to turn off or not use, stuff like this rasterizer discard. This literally discards everything you've just rasterized. And it's only useful if you have side effects from your vertex shader that you care about. Otherwise, you just set a false. I forgot it existed until I reread the tutorial earlier, and I was like, huh, I guess that is useful, but it definitely isn't getting a lot of use from what I do. So we have the polygon mode. The polygon mode is silly sounding because it's like, didn't we just set the rasters, the input assembly, the topology, which has a similar thing here? If we go to VK polygon mode, we have fill and line and point. So fill is for our triangles that we want to fill in, but we could use the polygon mode to rasterize triangles, but then only do outlines or points. There's more topologies than, you're asking, someone asked about triangle fans and strips. The primitive topology has way more than points, lines, and triangle lists, but those are the main ones that people use. So those are the ones that are being discussed. We have line width, set if you want to draw thick lines. Cull mode, this is for front face and back face culling. We're not going to use that yet, so we're just going to set our culling mode to none. Our front face is the direction of the winding of the vertices. There is way better descriptions of all of these things in other places, and I implore you, if you don't understand what they are doing here, to look them up, because I am not a good explainer on what these are. We're not using depth bias. We're not going to use this stuff, and then we can pretty much be done with this function as soon as I copy paste the definition. Multi-sampling is something we're not going to use in the tutorial. It allows multiple samples per pixel, but efficiently using hardware because it's a hardware feature. I need to copy paste that. Whoops. Quickly try to fix my past mistakes. Yeah, there we go. So we're just going to set basically everything to false and not have much of anything. There we go. So the color blend attachment, because we aren't drawing anything transparent, there's not much blending we have to do, if any at all. We also don't have multiple frame buffers that we're drawing to, so we don't have to worry about that. So everything here is mostly just the null aspect. Here we have our color write mask. We want to write everything, so we have to specify all 4 color channels, R, G, B, and A. We're not doing blending, so we turn that off. So we have all of these initializers we've just worked through. Now we can finally create our pipeline. So we'll have to add the pipeline builder function, which I'm going to put here because I put it at the top. Pipeline builder takes in a device and a render pass. We need to set the viewport. Even one thing we're doing in this tutorial is using dynamic viewport and dynamic scissor. So even though these values are not actually set in stone, we do need to specify them to be correct, and we're just going to use the viewport and scissor of the current frame size, but then we can change it in the future if we want. We need to set the color blending mode. We aren't doing anything, so we don't have much of interest in here. False, as you can see. So why did that? Oh, okay. So these do not have the initializers for them, so that's what's confusing me. So we can finish the pipeline builder class function. Sneeze. Okay, I didn't sneeze. Graphics pipeline, create info. Thick struct, and it contains references to all the other things. And for shader stages, it's going to be an array of shader stages. What is it? Stop messaging me. Where did the things get created? Oh, right. Okay, so I forgot about it. Since these structs are members of the pipeline builder struct, that means we can just reference them directly with, the address of to get the pointer to it. And those will be set by default. And to create a graphics pipeline, we call the graphics pipeline function. It actually can take multiple of them, but we're only going to do one right now. And we pass in the pipeline info we want, which is this struct here containing all of this. Here we set the render pass. The pipeline layout get built. Did I skip a chapter? I don't think I did. Oh, it hadn't created it yet. Okay, that was confusing me. Pipeline layout. So one of the bits of data that we provide the rasterization pipeline is the descriptors, and these are references to the textures and buffers that just exist in GPU memory. While we don't need to know the exact buffers and images that are used in this pipeline, we need to know the layout of those inputs. We create a pipeline layout object to describe those inputs, the buffers and images. Since we don't have any inputs yet, we can just create the null or the empty pipeline layout. We can see here that there's no flags, there's no push constants, which we'll use soon, and then there's no layouts, and these are descriptor set layouts. There's nothing, so it's empty. We will need to create a pipeline layout, and we'll put it in our main class, as well as we'll need a pipeline. So I might as well do that while I'm here. So there's a pipeline layout and the pipeline. So we need to create the pipeline layout before we can create the pipeline. So go away. So we will do it after in the init pipelines function, which I put down here. Do it after that. We use our VK check macro to make sure it succeeds. Now that we've created that layout, we can set everything we need in the pipeline builder, which is a lot of things. So our pipeline builder object, we create it, we add the shaders we need, and we're going to do a vertex shader and a fragment shader. You can correspond to the shaders we loaded up here, the modules that is. We set the vertex input with nothing because we're not doing anything with it. We have our builder for the viewport and scissor. We're going to use the window extent as our width and height for both of these. Our rasterizer, multi-sampling, color blend, and or just these three, we're going to use the initializers to make it. We have our polygon mode fill, so we're going to draw triangles and fill them in. And then we just create our pipeline, rebuild our pipeline. We have all of this builder code set up such that we can make more pipelines easily instead of having to respecify every struct. So if we run it, we should see a triangle, and it failed to build. Why did it fail to build? Render pass is undefined. Did I not make a render pass? Am I on the wrong chapter? I think I'm on the wrong chapter. Whoops. Where's my... halfway through chapter 1. Oh. That's embarrassing. I deleted the changes I made to the previous thing. So I'm missing stuff and it won't compile. That's embarrassing. But all you'd see is a triangle, a red triangle. I'll fix this up afterwards, the code base that is. That's right, we didn't actually add the rendering commands to it. So to use the pipelines we've just created, we need to go to the commands function, which records the commands, and I don't have it because I muddled up my own build. Okay, so there's not going to be any point in me showing code anymore because it won't build and it'll take too much time to fix it to do that. Come on, there. So I'll just try to explain what's going on. We need to add the command bind pipeline command in our command buffer recording function. We put it in between the begin and end render pass because we're going to use that render pass we begun. That's where this render pass thing will come into play. Now we can draw 3 vertices and we get a red triangle. This command draw takes in the command buffer. It says we're going to have 3 vertices and there's only one. What is the parameters for that? Bing pipeline? Did I misspeak? I definitely could have. Here's the parameters for command draw: vertex count, instance count. Oh, right. Since we're only drawing one instance of the vertex buffer, quote unquote, even though we didn't bind a vertex buffer. We only have one instance to draw. First vertex and first instance. This is saying the first vertex to use is the 0th, and the first instance to use is the 0th. It's a lot of work, but we finally got a red triangle on our screen. Now we can talk about passing data through the shader stages. There are inputs and outputs to the vertex and fragment shader, but they're not perfectly symmetrical. In the vertex shader, you can output whatever you want, and in the fragment shader, you can input whatever you want, but they have to match the type and location. So if we want to pass a color in from our vertex shader to our fragment shader, we need to define the outputs and inputs of our shaders. So we have our vertex shader, and we're going to define an output of out color, and in our fragment shader, we're going to have an input of in color. Oh, come on. Oh, there we go. So this and this have to match. They do not have to match names, though, which is very convenient for reading the code. They have to have the same position, and that's how it can validate that it's the same type there. So the interesting thing that happens between the vertex shader and the fragment shader is there are 3 vertices in a triangle, and we'll output a value to our out color here, which will be based off of an index into an array of colors. That way we have more than just red being drawn. But there are many, many, many fragments being run. It's not a one-to-one correspondence. We're not going to get a single one of these values. Like, we're not just going to get red or green or blue. What's going to happen is that the color here is passed out of the vertex shader, an out color, and then the color that gets passed in is interpolated from the 3 output colors of the 3 vertices, such that it will smoothly blend the 3 output colors based on the distance of the current pixel being drawn to the vertices. So this is how we can get smooth color gradients across the triangle surface. We'll have the 3 corners being 3 different colors, but each fragment rasterized will have its own blended color, which will result in a smooth RGB triangle. So I explained why that's something I found. The blending of those 3 coordinates is something I found to be not very well explained when I was learning graphics for the first time. So I want to be sure it was mostly clear. I've just updated the vertex and fragment shader of my own code. Okay. Oh, right, I didn't update this. To make use of the in color, we're going to just use it as the color that we want to output. GLSL has some fancy things for swizzling and converting vec3s, vec2s, and vec4s around. So here we can pass in a vec3 and a single float, and we can get a vec4 out of it, and we return that in our output. To change the shader code, we just need to recompile it. What I should have done is created a second file to contain these, because that's what the tutorial does. Because in the next chapter, we're going to enable toggling between the 2 shaders. And to do that, we need 2 different pipelines. We also need the shaders to be separate files and separately compiled. So if you follow the tutorial, you'll find you'll be copying and pasting this code. And I mean, you can use this right now to get a color triangle, but to make it switching, you have to do more. So we want to switch which pipeline to use, and by extension, the shader to use, and then finally the color that's going to appear on the screen. We need to have a way of telling our application when to switch shaders. We're going to use the space bar. So every time you hit the space bar, it switches between it. To get that input, we need to handle SDL inputs. Before, we were just checking if the SDL input is we need to close the window. What we should add is if the input is a key down event, we then check what kind of key it is. And if it is a space key, then we run the logic of changing the selected shader. Since we're going to have two, we could have some sort of toggle here, but for this, we're just going to add one to it. So you could have 10 shaders in an array, and this would allow you to index into it. You just have to go back to 0 if you hit 10. So this will just toggle back and forth between which shader you use every time you hit spacebar. Multiple pipelines, we'll create a second VK pipeline, and we'll call it red triangle pipeline. This will actually be the original one. The triangle pipeline will be the colored triangle pipeline. Here you can see the big fat wall of text is the different shaders that we're going to load. So we have color triangle, fragment, and then color triangle vertex, whereas here we have triangle fragment and triangle vertex, and we just put them into the right variable, the shader modules. We then are going to create a new pipeline. Because we've already set up all of the things in the pipeline builder, we don't need to start from scratch. We can just change what we have in the builder. So here we have our build pipeline, and this is going to set up our regular triangle pipeline. But to make the second pipeline, we're just going to clear the shaders stages, then add the shader stages we need with the correct shader modules. So we have red triangle, vertex, and fragment, and then we build another one. And so that this is why we did all that work to get a builder going. Makes it a lot easier to spam more pipelines. The last thing to do is to hook up the selected shader variable to the pipeline we want to bind. And here we have our triangle, and we have a red triangle pipeline, and we just change which one gets bound in our command buffer recording. Now we've done a whole bunch of stuff. We have quite a few objects which need to be deleted. Before, we would just delete them at the end of the frame, not the frame, the application. But there's a problem because we have to make sure that the objects are no longer in use before we delete them. We have to wait until everything is done being in use. The challenge is handling that in a cohesive manner. One of the best one of the better solutions for this problem is the concept of a deletion queue. In normal CPU programming, you delete something once you're done using it, and you oftentimes can know when something is done being used based off something like a stack frame. In C++, this is called RAII, and other languages have similar features where you can defer the deletion of something until a stack frame pops. Well, Vulkan is not a programming language, it's a GPU API, so there is no stack frame corresponding to it. What we can do instead, though, is put everything we need to delete into a queue so that at a later time we can go through this queue and delete everything in it when we know everything in that queue is ready to be deleted. And we're going to use a very simple structure to do that. It's not a very performant structure, but for what we need, it's generic and simple. And simple is the bigger thing. So we're going to have a DQ, which is a double-ended queue. It's just a container that you can push stuff on and then pop stuff from. Yes. when we want to add new things to be destroyed, we push a stood function. So instead of pushing on individual objects, we're actually going to push on a lambda, which is a function object thingy that then gets called at a later time. What that later time is that whenever we call flush, we iterate through everything in our queue and then call delete on it, or in other words, the function. Because it's a function pointer, calling the function will do the stuff in the function. And then we clear it saying we've cleared everything out so that the next time this flush gets called, only new things get deleted, new things added to the queue. We need to make sure we include the headers, dequeue, and functional. And so whenever we create something that needs to be cleaned up at the end of the application, instead of adding code to the cleanup function every time, we're going to push a new function onto the main deletion queue. We added the main deletion queue here. Someone asked why the dequeue was used. I'm not 100%, but a dequeue has good insertion and deletion. Is there a queue in the C++ standard library? I believe there is, but
there is.
Okay, I believe this one is it's like a vector in how it's implemented, but it's efficient for what our use case is. Is it it's not, the choice of container here doesn't really matter that much. It's not the most performant container, or this is not how you'd want to do it if you're deleting millions of things every frame. You really wouldn't want to do this. But the way it works is we have our function here. This is the lambda syntax of C++. We have our angle brackets. This equal sign signifies something specific. It does not need to be there, but not angle brackets, square brackets, parenthesis, curly braces is how we do lambdas in C++. Anonymous function is another name for this capability. It's in most languages these days. We call the function we want and we pass in the data. What this equal sign is doing is copying every local variable that's referenced in this function into the lambda context. So it's capturing everything by a copy. The alternate thing you can put here is a parenthesis, not a parenthesis, what am I thinking of? It's an ampersand. An ampersand means reference. We really don't want to do that because a reference can dangle and point to bad memory. And that's a really bad thing to have, is memory problems. So we want to copy everything. Because Vulkan operates on handles, we're pretty much always safe to do that, because the handle is just a integer and we just copy the integer. And that's all we're doing. We're not doing any crazy lifetime stuff there. In general, you want to copy in lambdas. You really don't want to reference unless you know what you're doing. We're going to refactor the code to make use of it. There are some things that we're not going to put in our deletion queue: the surface, device, instance, and destroying the window. But before we do that, we want to wait for everything to be finished. So on the last frame, we submit a command into the graphics queue, but we need to wait until it's done. Normally, the draw function waits at the very start of it. So now we're just effectively copying the very first bit of the draw function and pulling it into our cleanup to make sure that the graphics queue is finished executing. Once that's done, we can flush the main delete queue. That will flush everything, delete everything that's been put inside the main queue. Someone asked about copies everything in the scope. It copies referenced variables. How lambdas work are something that I implore everyone to look up on their own, because I think there are better explanations in this tutorial. And there's quite a lot of cool things you can do with them, but also a couple of foot guns in them. So when I say copy local variable, I mean copy variables that are outside of the scope that appear inside of it. So the function here, something, would be copied because it's a variable outside of it that's used inside. The reason it has to be copied is the reason we want to copy it is that when we call this function, this function will be called at a later time after the scope of this function has exited and this local variable has ceased existing. So we want to make sure that the values that are here in this local function are preserved so that when we call the lambda, which happens in our flush right here, those values are preserved and we can use them. You can explicitly name the objects you want to copy in the capture list. The square brackets here is the capture list of the lambda. We use equal sign because we just want to copy everything that is of relevance. So when we start refactoring things, here we have our swap chain. We want to destroy the swap chain. We use this variable here. This will get copied using this. So this is a good example of that copying. And then this function will get called when we call flush, which goes through the array of the DQ, calling all the things, calling the function. Now we do that same for the render pass and the frame buffers, and you can see how after we create the object, we immediately push on a deleter to the main deletion queue. We do the same for command queues, command pools, and sync structures, and it's a lot of copy pasting code. And then we can delete all the stuff that was in the cleanup function previously. And here we have the only exception to this delete everything at the very end of the application. So when you create a pipeline, the shader modules refer to binary code, the SPIR-V code, that gets copied into the shader, into the pipeline. And we do not need the shader module to exist any longer after we've created the pipeline. So we can immediately destroy all of the shader modules we've created. This is like one of the few objects you can destroy right after you've used it. Most everything else you have to wait until the very end of the application, like the pipelines and pipeline layout, which get added to the deletion queue. So this is actually out of date. I need to go update it, but that is everything we'll be covering this week. I wish I had my project set up correctly so I could copy paste everything so that I could show you the output and get it rendering, but no, I had to accidentally delete all that. So this is what you'd be seeing on my screen if it was working. So is there any questions? Feel free to type it out or get in voice, ask over voice if you'd rather. Because if there aren't any questions, I'm gonna say goodbye and end the recording. Well, if there aren't any questions, thank you for listening and thanks for watching. End the recording.